Good afternoon, everyone. Today we will begin a new course, Geomechanics for Geologists, and we will consider today lecture number 0, Introduction in Geomechanics. The summary figure shows the main tasks facing mechanism. That includes a full cycle from the exploration stage to the development of exploitation. These geomechanics tasks includes drilling optimization, including an assessment of the borehole stability, forecast of pressure, and losses zones. Of particular importance of the assessment of the reactivation of faults and fractures in discrete fracture model, clarification of the parameter hydraulic fracturing, prediction of sand production, assessment on the borehole stability, as well as the prediction of subsidence and compaction of reservoir and daily surface or seafloor. The geomechanics plays the most important role at the stage of refining drilling parameters and optimization of the drilling process. At the drilling stage, geological and technological complications are possible associated with the losses of circulation, large deviation from the vertical column, instability of the borehole, damage to rocks problem with cleaning of the borehole, etc. problem. A correctly constructed geomechanical model allows to reduce these risks and also reduce non-productive time and ineffective costs. The so-called uncertainty funnel on this slide shows how initial problems taken into account at the drilling design stage can snowball. They eventually lead to cost consequences in the form of stuck cement problem, lost circulation problem, poorly recorded logs, etc. All of this ultimately results in multi-million dollars financial losses can be. So let's discuss what a 1D geomechanical model, what is it 1D geomechanical model, and what its main tasks are. 1D geomechanical model is a model of mechanical properties and stresses built along a specific well. As a rule, this is a set of properties in the form of continuous curve. The main tasks of a 1D geomechanical model are to reduce drilling risks, prevent drilling events such as blowouts, stickings, tightening, and so on. The following tasks are to clarify the allocation of casing shoes, clarify the trajectory, and optimize the geometry and properties of hydraulic fracture. If we move from a well scale to field scale, geomechanics solves more complex problem here. In addition to the fact that it allows us to predict the stability forecast of design well of any trajectory, here we can also solve problems of refining the subsidence of the daily surface or seafloor, reactivation of faults and DFM, calculating the maximum allowable bottom hole pressure for the prediction of sand production, refining the integrity and other problems. Also, the volumetrical geomechanical model can be 3D and 4D. 3D geomechanical model is a static model of properties and stresses in a certain volume. A static model implies the absence of any change in the model over time. 4D geomechanical model is a 3D model with a change in certain time steps. This allows us to estimate change in stress strain during the development of the field. On this slide, the main data required to build a geomechanical model. The most critical ones are highlighted in red. Green and orange are optional data. The most critical data are logging, drilling information, geomechanical studies of core and cuttings, well testing, well investigation to determine the fracture closure pressure, hydraulic fracturing, breakdown pressure, pore pressure, and other parameters. L-00 correct mechanical properties, population in the interval space, seismic material as an inversion, interval velocities are needed in the form be in a deep domain. Also, microimager on oriented calipers, multi-arm calipers are very suitable for clarifying of the effect of maximum horizontal stress. On this slide, a typical workflow for building a 1D geomechanical model. This workflow includes the stage of analysis of initial data as well as a necessary calculation of mechanical properties and stresses. As you can see here, the stage of data analysis is very important for further work and also predetermines the correctness of entire geomechanical model. For a very detailed analysis of this scheme, select lecture number 8, which is called as Initial Data for a Geomechanical Modeling. So let's start analyzing the main problems that geomechanical solves. The first problem is to predict abnormal pore pressure. This is very important when drilling depth wells, especially exploration. It can cause serious drilling events, in particular fluid showings, increased gas readings, emissions, and so on. In order to make a pore pressure prediction, it's first necessary to analyze seismic data and identify velocity anomalies. The resulting velocity anomaly can be interpreted as pressure anomalies. In particular, the Ito method shown on the slide works on this principle. As we can see here on the right track, the curve change when the coefficient change from 1.2 to 3. The higher the coefficient of Ito, the more the PPG curve expands. Please pay attention to the example given on this slide. It shows the calculation of the abnormal pore pressure, and the recommendation are given to clarify the safe mud weight. As we can see, in accordance with the recommendation, the mud weight was increased by 15%. This is turn lead a decrease of gas showings and an increase in rotation of penetration. On the other hand, the excessive increase of mud weight can lead to losses because, as we can see from this figure, the safe mud weight diapason narrows significantly. This is confirmed in some other wells in which, after a certain distance, we see a step-by-step change in increased gas readings and losses. If we are talking about fields where depletion in pore pressure is observed, then in accordance with the stress pass effect, this leads to a decrease of SH mean, minimum horizontal stress. This increases the risk of mud weight losses with a greatly reduces of pore pressure. An obvious example would be drilling with the same reservoir with a difference of 10-15 years. When in the first case the reservoir was drilled at 1.15 gram per cubic centimeter, and after 10-15 years the same mud weight already causes losses. The geomechanical model allows one to predict quite accurately the range of change in the safe mud weight. An important task is to optimize the drilling trajectory, because a difference in deviation of several tenths of degrees can lead to a significant increase in the risk of borehole instability. For example, drilling of anisotropical clays at the angle of 30 degrees and at the angle of 60 degrees. There are already significantly different drilling conditions. Therefore, the geomechanical model allows to design the casing and inclinometry of the well in such a way as to avoid extremely high breakout pressure and not case the risk of sticking. As shown as a figure on this slide based on the model of offset well interval of various drilling events and risk are indicated in advance on planned well, as well as measured to identify, control, and eliminate them. A correctly calculated geomechanical model allows predicting the breakout pressure and breakdown pressure, which depend on the well survey, and predicting the static and equivalent circulation density window. All advanced information about breakout and breakdown pressure you can find in lecture number 6 and number 7. Please note that during drilling the static mud weight increases to the level of ASD. This explains the fact that as a rule during drilling the well is stable. During backreaming out of hole and drilling stops, the mud weight decreases to the static level, which very often leads to a decrease in static mud weight relative to the collapse or breakout pressure. Because of this, we observe breakouts and washouts at the backreaming out of hole stage and the wireline stage. An excessive increase in the ESD during drilling can provoke the faults and already existed fracture reactivation and lead to the losses. To reduce risk, geomechanical support of drilling in real time is also used. The essence of the process consists in a continuous reset of update with some mail server. This data are constantly updated in the software and allows updating the model to the current bottom hole. Often logging data is carried out during the drilling process, including acoustics, which allows to see the start zone of HRP and time and make a decision to stop or continue drilling. For different stress regimes with different ratios of principal stress, the most stable well trajectories will be different. For example, for a normal stress regime, the most stable well will be well with a small deviation from the vertical in direction of SH mean. For a reverse fault stress regime, the most stable well will be a horizontal well in the direction of SH max. And if you look at the strike slip regime, then the stable direction will be in 4 azimuth, and the most unstable well will be vertical. The sensitivity analysis can be used to calibrate the geomechanical model and refine the SH max. The essence of sensitivity analysis is that the reference layer is taken. All drilling events, well survey, and other materials are analyzed for borehole instability. For each well, the breakout shear failure gradient is calculated for the reference layer and compared with the actual data. Well points in radial coordinates of deviation and azimuth uploaded on the StereoNet on the right. Sensitivity analysis is carried out until the behavior on the StereoNet corresponds to the actual points. Points are highlighted in different colors depending on intensity of collapse. The red are strong collapse, yellow and green moderate and minor collapse. The next task facing geomechanical model is to refine the parameters for prediction hydraulic fractures. The geometry of the hydraulic fracture depends on the contrast of the minimum horizontal stress at the reservoir and seal contact, as well as the elastic properties and permeability. These parameters can be calculated from a geomechanical model. SH mean can be calibrated to XLOT, in particular to the fracture closure pressure. Elastic properties and permeability can be calibrated to the core investigation data. The geomechanics also successfully solve problem with the development of unconventional reservoir. One of the tasks is the creation of additional permeability in initially impermeable rocks. An example of unconventional reservoirs are a formation at the Bakin, Barnett, Bajenov, and another. The geomechanical modeling allows to identify as the so-called sweet spot zones, which are more interesting from the point of view of creation artificial fracturing in them. The zones should be brittle, that is, it should be possible to create hydraulic fractures in them with subsequent fixation of probing agents in the interfracture space. Ductor interval usually refer to barriers, and such parameters as the Rickman brittleness allows to identify the most brittle intervals and place hydraulic fracturing ports on them. Taking into account the properties of the well casing, in particular the metal with the well structure is made, allow us to predict the integrity limit of this casing. This is especially true for fields with a high tectonical and seismic activity. The damage of casing can lead to premature failure on the well due to various overflow in the column space, cement disintegrity, and other factors. The discrete fractures and faults are also typical for zones with high tectonic activity. Their reactivation of faults and their displacement is especially dangerous. Absence of taking into account the properties of faults can lead to losses during drilling, damage of the wellbore casing, activation of reverse fault and normal fault, and other effects. This slide shows the reactivation of faults over time. Non-reactivated fault cells are shown in white, and reactivated fault check are shown in red, for which more circles goes beyond the failure criteria. It's the same for discrete fracture net, DFN fractures. Another problem is sand production in wells. Geomechanical model also to calculate sand production potential maximum allowable bottom hole pressure and critical drawdown pressure to avoid sand production, and also to predict at this time and in which year the sand production will begin. In this example, the 5 wells are shown in which the stress field and sand flood change by years. This model also allows to reduce the risk of sand production and reduce risk for erosion of facilities. On this triangle, the different probabilities of sand production prediction are shown color zones. The green zone is a low probability of sand production. From yellow to red, a higher probability of sand production. As you can see here, over time the boundary of color zone change. This is due to the decrease of pore pressure over time. This analysis allows us to understand in what time period sand production is predicted. The 3D geomechanical model allows calculating the maximum allowable bottom hole pressure and avoid the sand production for any arbitrary oriented well trajectory. This slide shows change in maps for different azimuth and wellbore deviation from azimuth 0 and deviation 0 to azimuth 180 and deviation 90. As we can see here, there is an increase in the deviation, the breakout pressure increases. This means that in the wells with a large deviation from the vertical in a given stress state, the probability of sand production will be higher than in vertical wells. At the same time, if we look at the well with the same deviation in the direction of the minimum and maximum horizontal stress, the probability of sand production will be higher in a well drilled in the direction of SHmax. Please note the processes of daily surface subsidence and reservoir compaction. This is very critical to take into account, and this is also the tasks of geomechanics. It allows to estimate maximum allowable deformation for estimation of daily surface subsidence, because also the wells and platform squares have a maximum permission to subsidence, and it be must into account. When managing the project involving carbon capture and storage, it's very important to estimate the seal integrity. To avoid carbon dioxide breaking through the seal of fault fractures to the daily surface, 4D geomechanical modeling is carried out, which allows assess the properties change of the seal and determining of maximum allowable volume of carbon dioxide injection into the reservoir. The similar problems are solved when analyzing the work of water injection wells, where it's also important to understand the strengths of the seal and the reservoir, identify out-of-zone injection areas in order to increase the oil recovery coefficient. Thank you so much for attention. If you have any question, please write me in my email.